All right, and so using implicit differentiation like this actually allows us to be able to talk about inverse trig functions, which we haven't seen yet. Um, we've talked about how to be able to do a trig functions like sine and cosine, but not the inverse sine, or you might think about the arc sine. And so let's look at just the arc sine, and then we'll see kind of with all of the other trig functions too, how can we deal with those in pretty much exactly the same way. So let's say you have a function like y equals the arc sine of x. And again, really what we're just doing is building up our library of derivatives. So once we look at the inverse trig functions, you can go ahead and put those on your list of common derivatives that you might see show up that you should know about. So keep in mind that when you have something like y equals the inverse sine of x or the arc sine of x, here's what that means. That really means that sine of y is equal to x, or at least for specific values of y. You got to be careful because remember what you're allowed to plug into where you have a restriction on the inverse sign over here is that you're not allowed to have values outside of negative pi over 2 to pi over 2. So you may remember that from a past class, either trig or pre-calc. But what we're going to focus on in this idea of finding a derivative is this equation right here in the middle. And the goal is, can we find y prime when you have an equation that looks like sine of y equals x? Because remember, our original function is y, we're trying to find the inverse of that, or I'm sorry, the derivative of that. So go ahead and take that equation and take the derivative of both sides, d over dx of the sine of y, and then d over dx of x. Okay, the right side's pretty straightforward. That is just 1. The left side, we can take the derivative with respect to x. Again, remember, because there's a y inside, it's like a chain rule. We need a cosine of y, but then times a y prime. Okay, so we can do a little bit of algebra here. Our goal is to get y prime all by itself. So that's pretty straightforward. Go ahead and divide both sides by the cosine of y. And what we can do with this, if we look at the cosine of y, remember where y is. Y is supposed to be between negative pi over 2 and pi over 2, which, if you think about your unit circle, I know for some of you it's been a while since trig, negative pi over 2 to pi over 2 is either in quadrant 4 or in quadrant 1. That's where y is. But we're looking at the cosine of y here, and so the cosine of y, either in quadrant 4 or in quadrant 1, we're going to the right. That means cosine has to be a positive value. So when we're talking about a positive value, you might remember something that says, you might remember something that says that the cosine squared of y is equal to 1 minus the sine squared of y. That comes from your Pythagorean identity. And if you go ahead and take a square root of both sides, you get the cosine of y is equal to the square root, and you would have a plus or minus square root in there of 1 minus the sine squared of y. Okay, but the difference here is that we don't need a plus or a minus in here because we know we're either in quadrant 4 or in quadrant 1 where cosine is positive. So really the cosine of y is just the positive square root of 1 minus the sine squared of y. And you might say, well, why are we doing this? Well, what we'd like to be able to do is this. We'd like to be able to rewrite this to get back to talking about x, not having a y in it. I don't love the fact that there's a y right here. So if we can get back to talking about an x, that would be good. So we have y prime equals 1 over the cosine of y, but cosine of y is supposed to be the square root of 1 minus the sine squared of y. Okay, and not just a plus or minus square root, but just the positive square root because of where our restriction is there. Okay, now how is this helpful? Well, look at what y is. Okay, y is the inverse sine, or the arc sine, of x. All right, so y is the arc sine of x, and so another way to write this is to substitute back in for y. Like I said, we want this to be in terms of x, not in terms of y. So we get 1 over the square root of 1 minus the sine squared of y, which is the inverse sine of x. Okay, and so another way to write this with this sine squared is to write it as the squared on the kind of the whole thing here. The sine and the inverse sine there are going to undo each other, and you're just left with something like 1 over 1, the square root of 1 minus x squared. and this is what the derivative of your original is equal to. So this is a little bit of work. We got to be careful about inverse signs and where the restriction is, but basically the idea here is we're going to use the inverse sign to kind of convert over to talk about the sign of y, so that we can take the derivative of both sides of the equation, and then once we've done that and we have in the derivative equation, we want to get y prime by itself, and then if we can convert that derivative equation, instead of having y's in it, to now only having x's, then we can say, hey, if we know what y is, we know what y prime is, and everything only has an x in it. So in case that was a little bit unclear, here is kind of what we're saying at the end. This is our final conclusion of this. When we start with an arc sine or an inverse sine of x, and we take the derivative of that, what we end up getting is 1 over the square root of 1 minus x squared. Okay, and if we looked at the inverse cosine or the inverse tangent or the inverse secant and cosecant, other ones actually look a lot like this. Okay, so I'll go ahead and kind of write these out. Again, you can actually walk through these in a similar process to what we did before, using implicit differentiation for each of these. The inverse cosine looks really similar. It's equal to, or I should say the derivative of the inverse cosine is 1 over a square root of 1 minus x squared, but it's a negative out in front. And if you have an arc tangent or an inverse tangent here, and you're taking the derivative of that, you actually get something like 1 over 1 plus x squared. To be quite honest, from my experiences, out of all of these inverse trig functions, the inverse tangent might show up the most, even more so than talking about an inverse sine or an inverse cosine. Okay, so, and then you could talk about the inverse cosecant. The derivative of that looks like a negative 1 over x times the square root of x squared minus 1. Okay, and then the inverse secant, the derivative of that one would look like 1 over x times the square root of x squared minus 1. If the sine and the cosine are basically the same but off by a negative, it shouldn't surprise you too much that the secant and the cosecant are almost exactly the same. They're off by a negative. And in fact, the cotangent as well, the cotangent inverse, the derivative of that is also very, very similar to the inverse tangent, which is a negative 1 over 1 plus x squared. Okay, so these are good ones to have in your bag, that you can pull these out and kind of be able to deal with derivatives of inverse trig functions as well.